Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. Welcome to Electronics. I am Madam Rosmina Zuin Abdul Rahim. First, let's have a look on this hadith. Muawiyah reported, the Messenger of Allah sallallahu alaihi wasallam said, "If Allah intends goodness for someone, He gives him understanding of the religion." Source Sahih Al-Bukhari. I'm highlighting this hadith to you because being students of knowledge, first and foremost, we need to understand the religion. Then after we really understand our religion, other knowledge will become easier for us to understand. Then Allah mentions here that if He intends goodness for someone, then only they will make them understand the religion. Meaning we have to pray for it, ask Allah to give us the understanding of religion, because it's the goodness coming from Allah. In this video, we are still on chapter 6, FET Intro and DC Analysis. And basically, this video is about chapter 6b, which relates to the DC analysis, where it can be divided into two subtopics. The first one is for the source grounded as well as on the DC load line, and the second one still on DC analysis, but this time for source is not grounded, as well as when we are having current source in the circuit. Okay, as a start, let's have a look on the basic of DC circuit analysis for NMOS. So as can be seen here for NMOS circuit, we have the drain, gate and the source, remember, for the NMOS. So for the drain, gate and the source, as you can see from here, actually we have GS loop. Okay, GS loop actually indicates the input loop, and we have DS loop, which indicates the output loop. Okay, and for this particular circuit, the source terminal is at the ground, as can be seen here, and as you can see here, the source actually is common to the input as well as it common to the output. And another thing that we should take note is when we are having capacitor similar to BJT circuit, when we are considering DC analysis, this capacitor can be replaced with open circuit, meaning we are disconnecting the AC signal from our DC analysis circuit. So from this particular original MOSFET circuit, now we can have this kind of circuit because we are omitting the capacitor, replaced with open circuit. Then as can be seen here, first thing first, you should take note that always the current at the gate is equal to 0. Current at the gate should always be equal to 0. Because why? There is an outside layer at the gate, remember? Okay, so there won't be any current flow. So the only current at NMOS transistor will be the ID, which is also equal to the IS. Okay, so that's why normally IS is also called as ID, because it is just the same current. Okay, then another thing that you should take note is from here, actually we can consider voltage divider principle for us to find for the Thevenin equivalent circuit. Remember, similar to voltage divider biasing for BJT, because we have about the same arrangement where we need to find for the VTH and RTH. So for this particular VTH, it is actually equals to VG. Okay, then it's actually given by this voltage divider principle. Then how do we do the DC analysis of NMOS circuit? Basically, there are 5 steps that we need to follow. The first step will be to determine the value of VGS. We need to calculate the value of VGS. So as can be seen here, VGS is actually equals to VG, right? Since source is grounded, and VS equals to 0. So in this case, VGS actually equals to VG, which can be given by the VTH formula just now that we discussed in previous slide. And second step, normally we assume the transistor is biased under saturation region. Because of that, we can use this formula. Remember, in previous slide, we are considering two regions. There will be non-saturation region and saturation region. For non-saturation region, there is a specific formula for ID. For saturation region, this is the formula for ID. So since we are assuming this transistor is biased under saturation region, we can use this ID formula and substitute everything so that we can get the drain current value. Then only for the step 3, we use KVL at the DS loop. Okay, this is the DS loop. So we use KVL because we already know the value of ID. Then we do KVL. From there, we can calculate the value of VDS. And step number 4 is for us to calculate for VDS saturation, which is given by VGS minus VTN. VGS, which we already calculated in step number 1, and minus VTN, which is the threshold voltage. Okay, then since in step number 2 we just assume that the transistor is biased under saturation, right? So step number 5 would be we want to confirm our assumption whether it is correct or not. Okay, so we need to check because we are assuming it's under saturation region, meaning the VDS value should be larger than the VDS saturation. Remember the IV curve? Okay, where it starts to enter the saturation, the VDS value at that time is equals to VDS saturation. So by right, if you are saying our transistor is operating under this region, the VDS value should be larger than VDS saturation, which is given by VGS minus VTN. From there, you can check whether the assumption is correct or not. To understand better about DC analysis, about the 5 steps that we have gone through just now, let's have a look on this particular example. For this example, you are considering NMOS, and R1, R2 are all given. RD is also given. We have VDD, VTN, remember the threshold voltage, and KN value is also given. Then remember step number 1, we are supposed to calculate for the value of VGS, right? Using the voltage divider, because in this case, VGS is actually equal to VTH because there is no current flow through the RTH, right? There is no voltage drop, so straight away we can say VGS equal to VTH, where we can do voltage divider, substitute everything. From there we can get VGS actually equals to 2 volt. Then we come to step number 2, where we assume the transistor is under saturation region, so that we can use this drain current formula where ID is given by Kn times VGS minus VTN squared, and substitute everything. Okay, Kn given, VGS you already found from step number 1, VTN given as 1, so substitute, you are getting ID is 0.1 milliampere. Then step number 3, we do KVL. Remember, we can do KVL here at DS loop. So from there we get IDRD plus VDS minus VDD equals 0. So rearrange it, you are going to get VDS equals 3 volt. Okay, then step number 4, we need to check what should be our VDS saturation value, which is given by VGS minus VTN, where VGS is 2 from step number 1 just now, VTN given as 1, so from there we know VDS saturation is 1 volt. Okay, then step number 5, we need to confirm our assumption. Since we are saying it's under saturation, the VDS value for our circuit should be larger than VDS saturation. So we check with the VDS value is 3 volt. Obviously, it's larger than 1 volt, the VDS saturation. So we can say yes, our assumption is correct. The transistor is under saturation region. So this is the ID, this is the VDS. Okay, let's have a look for the second example. For the same DC analysis, in the case of source is grounded, it's just similar example to the one that we discussed earlier, where in this case all the resistors values are given, VTN is also given, and as well as KN. In this case, you are supposed to find for ID and VDS. Okay, so remember all the 5 steps. So basically what you have to do, just to do all the 5 steps, remember. So the first one is to find for VGS, which is obviously given by VTH, when you can do the voltage divider, from there you can get VGS is actually 3.636 volt. Okay, because VGS equals to VTH, the Thevenin voltage. Then second step will be we assume the transistor is under saturation region, where from there we can use the drain current formula, ID equals Kn times VGS minus VTN squared. Substitute everything, we are supposed to get the ID value. Then step number 3 will be to do KVL at DS loop. So we do KVL, substitute everything, we can get VDS value. Obviously, step number 4, we check for VDS saturation. In this case, is given by 1.636. Then step number 5, we need to confirm our assumption. So we say, oh, VDS is larger than VDS saturation, right? Because 3.31 obviously is larger than 1.636 volt, meaning yes, our assumption is correct. So whatever ID value and whatever VDS value that we are getting, yes, that will be the answer, where ID is this value, VDS is this value. Okay, let's have a look on another example. Still, when source is grounded, okay, you know the source is grounded because it's connected directly to the ground. In this case, let's see when our assumption is wrong, is incorrect, what should we do? Okay, so if we have a look on the circuit parameters, all the parameters are given, VTN, KN, all the resistors. So obviously from here we need to calculate for ID and VDS. So as usual, we start with step number 1. When we do KVL at GS loop, basically we do the voltage divider, remember, where VGS equals to VTH, right? So if we do voltage divider principle, VGS you are supposed to get equals to 6.12 volt. Okay, then step number 2, we assume transistor is under saturation. So we use the ID formula, substitute everything, we are getting ID is 0.85 milliampere. Then later, step number 3, we use KVL at DS loop, substitute everything. At the end, you are going to get VTS equals to 2.9 volt. Then step number 4, remember, calculate for VDS saturation. In this case, VDS saturation is this value. Then step number 5, confirm your assumption. In this case, you notice your assumption is incorrect. Why? Because at this time, VDS obviously is less than VDS saturation, which is 5.32 volt. Okay, meaning our assumption that we are saying the transistor is under saturation region is not correct. Okay, so what you have to do, you have to start all over again with a new assumption. So as you can see from here, we go back to step number 2, because step number 2 we do the assumption, right, where we are saying the transistor is under saturation. Then we know it's wrong. Now we need to assume it's under non-saturation. Obviously we need to use this ID equation, the formula for ID, drain current. Okay, then what we have to do, substitute everything, because Kn given, VGS already we know from step number 1, VTN also given. Okay, then leaving our ID. Okay, leaving our ID is in terms of ID. Okay, because okay, you should notice that in this case, VDS is given by 8 minus 6 ID. Remember the KVL at the DS loop? Okay, we get this equation, right? So we substitute VDS in terms of ID into this equation. Okay, leaving the only unknown that we have here is ID. Okay, we are only have ID as the unknown. So we rearrange, okay, substitute everything, rearrange. Okay, at the end, you are supposed to get equation in this form, in the quadratic equation, where we are having ID squared and ID. Okay, so obviously for this quadratic equation, if you calculate from the calculator, you are supposed to get two values, right? So if you calculate, in this case, you are supposed to get ID equals 0.75 milliampere, and another value of ID is negative 0.78 milliampere. Okay, so which ID you should use? Obviously the one which is the positive ID. So we take ID equals 0.75 milliampere. Then from there only we go back to the DS loop and substitute, because we already know the value of ID. Now our VDS value is 3.5 volt. Okay, so from here we don't have to check our assumption again, because obviously there are only two possibility. The first possibility is already wrong, so obviously this should be our answer. This is the ID, this is the VDS that we are looking for. Okay, then there is another subtopic that we have to consider, which is the DC load line of the NMOS. Okay, if you remember, we talked about BJT before. BJT also has its own DC load line, so the same goes to the NMOS. Okay, in NMOS, the DC load line analysis will be the ID versus VDS. Okay, obviously in this case, you need to do KVL at the DS loop. Okay, to get the equation. Okay, we do KVL, then obviously we need to rearrange the equation in the form of y equals mx plus c. Remember, because our graph is ID versus VDS. Okay, then remember we have all this curve. Okay, the non-saturation and saturation region. So obviously ID as the y, x as the VDS, and the slope is -1 over RD, and the C, the y intersection, will be the VDD over RD. Okay, but other things is just similar like BJT, where once we have this equation, we can get the 2 points. Remember, when ID 0, what will be the point, and when VDS is 0, what will be the point. So you can have the 2 points, connect them together. Okay, the intersection of the straight line to the curve would give you the value of the VDSQ, VDS related to the Q point, as well as the ID related to the Q point. As I mentioned just now, it's just similar to BJT before, right? If we talk about BJT, where we have IC versus VCE, okay, where we find for the first point and the second point, get the straight line, then the intersection will give us the value of IC and VCE. So the same concept can be applied for the NMOS, where the curve will be the between ID versus VDS. Then you get the 2 points, remember, as I mentioned just now, and the intersection will give you the value of ID and VDS. It's just about the same thing. Okay, now we come to the third type of DC analysis, where the source is not grounded. The source is not grounded. Okay, so let's have a look for this one particular example. In this case, all the resistor values are given, and if you notice here now, instead of having source directly connected to ground, for this particular example, at the source we have RS. Okay, we have RS at the source. Okay, now we look how are we going to do the DC analysis of it. Okay, for the DC analysis for this particular type, where the source is not grounded, we can still apply the same 5 basic steps in DC analysis. The first one, obviously, we calculate for the value of VGS, remember? Okay, but in this case, we cannot straight away say VGS equals to VTH anymore. Alright, why? Because we already have another voltage drop, another component where we need to consider the voltage across RS. Okay, so for this particular example, you need to do kind of KVL at the GS loop. Remember, we have the drain, gate, and the source. So this is the GS loop, where we consider the KVL equation plus 1, okay, plus 0, because remember IG is 0, so there is no voltage drop across RG, plus VGS, okay, and plus IDRS, which is this one, minus 5, okay, equals to 0. This is our KVL equation. Then later our VGS will be in the form of ID. We cannot get a fixed value, okay, but our VGS will be in the form of ID. It's okay. Then we just straight away proceed to step number 2. The same thing, we assume the transistor is under saturation region, remember, then we can use this ID equation formula. We substitute everything, but for the VGS, we can straight away substitute VGS in the form of 4 minus ID. VGS equals 4 minus ID. Other components we just straight away substitute. Then if we rearrange this equation, it will be in the form of the quadratic as well, okay, in quadratic form as well. So what you have to do is you are supposed to get two answers, right? Okay, two possible answers. In this case, we are having ID equals 6.646 and ID is 1.354. okay, but the question is which ID should we choose? Okay, we don't know, okay, we cannot say because this one is larger current, so we choose this one. No, what you are supposed to do is you need to replace this both ID values in VGS equation in step 1. okay, so remember VGS is given by 4 minus ID, so both ID values you substitute, and in this case for the first value we are getting VGS is negative 2.646, and for the second value we are getting VGS equal to 2.646, negative and positive. So obviously in this case we choose VGS, which is 2.646, because obviously when VGS is negative, it's less than the threshold voltage. At that time the transistor is still off. Then once we identify our ID value, obviously we can proceed with step number 3, where we use KVL at the DS loop. Okay, be careful now, our DS loop won't be that straightforward anymore, because we have to consider whatever components inside the DS loop. In this case, remember we have this one positive 5, meaning positive at this side and negative is grounded, right? And negative 5 here, meaning negative 5 is connected at this particular node, while positive is grounded, meaning to say you have to consider both this 5 and this 5 in our KVL equation. So if you go through this loop, you're supposed to get negative 5 plus IDRD plus VDS plus IDRS minus 5 equals 0. Okay, so that's why we're getting this KVL equation. So from there you can just substitute, because we already know the value of ID. Then lastly you are supposed to get VDS value, in this case 5.938 volt. Okay, then step number 4, remember, calculate for VDS saturation as usual. We get this VDS saturation. Then step number 5, we check whether our VDS is larger than VDS saturation to confirm whether our assumption is correct or not. In this particular example, yes, our assumption is correct. Okay, then we need to consider this question as well, because this is a kind of design question. Okay, where in this case the VTN value is given Kn is given, VDD is given. The thing is, R1 and R2 values are not given, even RD is not given. Okay, meaning to say you are supposed to design the circuit by finding all the missing parameters, missing circuit parameters. Obviously, in this case, you need to find for the value R1, for the value R2, as well as for the RD. And ID is given, where VDS is also given. Then you need to confirm any assumption that you already make during your analysis. Okay, for previous example, I reserve for you to do your own self-revision. Then maybe we can discuss later because all the final answers are given. Okay, then we come to another example here which I need to highlight because for this particular example, this transistor circuit is using current source. Okay, meaning in this case we cannot do a conventional KVL equation like we always do. And let's see what are the parameters given, where VTN we have here, Kn also given. In this case we are supposed to calculate for VGS as well as VD and VS, and we need to confirm any assumptions that we make. Okay, then basically let's have a look on the circuit. At the gate we have RG, at the drain we have RD, but at the source, as you can see here, we have this current source. When we have current source like this, it means that the drain current has been set for you. Okay, automatically from here we know that the drain current is 0.5 milliampere. Then let's try to follow all the 5 basic steps that we do for DC analysis. For step number 1, we are supposed to calculate for the value of VGS, right? Then normally we do some kind of KVL equation, but in this case we cannot really do because we don't know the voltage across the current source. Okay, we don't know what should be the voltage here. So it's okay, we proceed to step number 2, where we assume the transistor is biased in saturation region, and this is the ID equation for saturation region. And remember, since ID is already given, straight away we substitute, meaning from here the unknown that we don't know is VGS, right? So we solve for this, and in the end we are supposed to get VGS equals 1.5 volt because ID is already given. Then step number 3, we use KVL at DS loop. Okay, but again we don't know what should be the voltage across our current source, right? What we have to do is we need to use some kind of branch current equation. Okay, so for example, in this case, this is the drain, this is the gate, and the source, right? Then here we have VD. Okay, VD meaning the voltage at the drain with respect to the ground. Where is the ground? Remember, we have -5 here, meaning negative is connected here while the positive one is grounded. This is the ground. So this should be our VD, and at the same time the node voltage VS is here, where we have the voltage from the source with respect to the ground. So this is our VS. Okay, then for the VD just now we can say from the branch current equation, it is this is ID, right? So ID is 5 minus VD, because voltage at the drain, over RD, right? ID equals 5 minus VD over RD. Then since we already know the value of ID and RD is given, so from there we can actually calculate for the value of VD, the drain voltage. Okay, then let's consider VDS is actually VD minus VS. VDS is actually VD minus VS, right? So how can we find VS? Remember, VG is 0, right? Remember, VG is 0. Why? Because it's connected, the gate is connected to the ground and there is no current here. Remember, IG is 0, right? So as if the gate is connected to the ground. So in this case we can say here actually VGS equals to VG minus VS. VGS equals VG minus VS. Since we know VG equals 0, so our VS is actually equals to negative 1.5 volt. Okay, negative 1.5 volt. Then from there, obviously, we can calculate for VDS value because we already know the VD, we already know the VS now. So from there, we can calculate for VDS, which is given by VD, which is 2.5 volt, and minus VS, which is negative 1.5. Okay, sum it up together. We are supposed to get VDS equals 4 volt. Okay, then remember in this particular question, you are supposed to confirm any assumption that you make. So obviously we need to consider these two steps, step 4 and 5, where we check for VDS saturation. In this case, it's given by 0.7 volt. Then when we check, obviously our VDS, which is 4 volt, is larger than 0.7 volt, meaning our assumption is correct, where we are saying the transistor is biased under saturation region. So I think that's all for this video where we discuss few examples related to DC analysis. Okay, I hope you understand this part very well because it's kind of important for you to know how to do the DC analysis for various kind of NMOS circuits. Okay, I think that's all. May Allah bless whatever knowledge that you have gained from this video, and may Allah make you closer to Him by having more knowledge, because remember, the true knowledge is the one that should be bringing us closer to Him. Okay, so I think that's all. Thank you very much. Bye.